started on the workshop, I just want to say a few words about the Institute. We were founded in 2012 with a generous grant from the Simons Foundation, and so we've actually not had to depend on federal funding, which makes us a very good place to be at the moment. And we bring together, as you know, we're the unique institution in computer science that brings together researchers for long collaborations. Of course, many of you are here for a week, but typically we have people staying for the entire semester so that we can actually begin collaborations. And our mode of operation is often to have, a very strong theory component in anything we do, but combining it with other perspectives and maybe providing fodder for new areas for theory to be working on. So, and this program is a very good case in point where we need, new models in theoretical computer science, new algorithms, and new, maybe lower bound techniques for understanding current architecture. And parallelism is a big piece of this as Moore's law is coming to a halt. And so this workshop on managing parallelism is very much an area where I'm hoping that we will have more realistic models of theory. I guess there have been some attempts, but we're still looking for a really great model for thinking about parallel computation, and maybe this will emerge from this workshop. So without further ado, let me hand off to Kirk, the organizer of the program, as well as this workshop. And
all right. So without further ado, our first speaker will be Jakub Lacki, who will speak on massively parallel computation in theory and practice.
Thank you. Thank you very much. It's really great to be here. I realized that I first visited Simons Institute when it was maybe 3 times younger than what it is now, and I very much enjoyed coming back since. In this talk, I would like to present the work, I would like to present our, but also works of others on running or solving very large problems in a distributed setting. Specifically, the setting in which I like to work is designing algorithms that go beyond the established models for analyzing algorithms, but actually looking also at the specifics on the underlying hardware and systems. And this way, I believe, the most scalable solutions can be designed. This talk is going to walk us through several examples, things that did work, things that did not work as well. The big goal that I would like to have in mind is that we would like to solve very large-scale problems fast using simple, fault-tolerant, and cost-effective algorithms. So let me unpack it. By fast, I mean we're looking for solutions that are fast in practice, not just fast with respect to the model in which you're working. Simple is important because I work with large graph problems daily, and we do implement graph algorithms. They should better be fast because otherwise maintaining them is not an easy task. Fault tolerance I will talk about in detail a bit later. And cost-effective means that a very common setting in which we operate in is that we do not have a supercomputer at hand that we can use ourselves. We actually work in a shared environment where there is a shared pool of machines that many users are using at the same time, and we would like to optimize the overall cost of running multiple computations at the same time. The focus, and as a member of a graph mining team within Google Research, I work on large-scale graph algorithms. And as you know, graphs do get very large, and they grow even bigger every year. Up until recently, the largest publicly available graph was the hyperlinked 2012 graph with over 200 billion edges. In 2018, we already published a paper that was working with a graph of 6.5 trillion edges. And if you were to present the problem of deduplicating training data for a large language model, you can easily figure out, based on public data, that as a graph problem will be a problem on a graph of over 100 billion edges. So these problems do appear and are actually important even this day. All right, so let's take a look at the motivation of what I mean by low cost. This is a plot showing resource usage, I believe it's RAM usage, in a production cell in one of Google data centers. This is from a paper published a few years ago. If you look at this figure, you have some high priority jobs that take maybe the third of the capacity, and those are the jobs that you really absolutely must run, and you don't want to lose any of them, maybe because they're serving user traffic. There is some part of capacity used by some lower priority jobs. Think of just someone running a one-off experiment. If it crashes, it's not too bad. That also takes a significant fraction of the capacity. But if you look at the top, you see that 40% of the total capacity is unused. And this gives a very natural idea that, well, let's try to use those unused resources in some way, because that's just free compute, right? So let's try to use it the best possible way. Now this is averaged over the whole, over multiple machines in a single cell. So it's not that you have like 40% of machines that are sitting idle. It's more like 40% of a machine on average is idle at a moment. So this is of course a great idea. We can use this capacity at low cost. Otherwise, in some sense, it would have been wasted. But on the other hand, this also creates some significant challenges. If you run using those low priority resources, your job may be preempted at any time because maybe the allocation changes. Now on the machine that you were assigned to, the usage of high priority jobs goes up. Your job is selected as the one to be preempted. Your computation is lost in the middle. So we need to assure some form of fault tolerance, such that if some of the machines that you're using for your computation, if they get preempted, you do not lose all the progress, but you actually lose as little as possible. The other issue working with low priority resources is that you don't get the whole machine to work with, but you actually get a small fraction of a machine. So maybe you get some number of CPUs, but even using that may be tricky, because what if you got 20 CPUs but almost no memory bandwidth? Those are the challenges that actually make it even trickier to design solutions in this space. Okay, so this was the motivating intro. So what I'd like now to talk about is, first, I'd like to present a couple of very well-known distributed computation frameworks that work in this environment. Then I'm going to discuss the Ampc and Ampc models. So those are some theory models that are that are designed to capture computation in a setting like this. And then beyond that, we're going to look at what's next, what are the shortcomings of the current solutions, and what are some possible directions to study for the future. All right, so a very well-known framework that works in an environment like the one presented is MapReduce. It celebrated its 20th birthday last year. And even though I know some of you may be familiar with the theory modeling of MapReduce, let me actually present how the actual framework works. I think this is informative to understand. If you know it, don't worry, it's going to be just a slide or two. So let's quickly go through this. The input to a MapReduce computation is a collection of typically small input records. And what the user needs to provide is first a map function. The map function takes all of those records, and for each input record, it produces a collection of key value pairs. It may produce multiple for one input entity. It may produce 0 for one input entity. It's all customizable. And this map is, of course, applied to each input entity separately. Once you produce those key value pairs, there is a group by key operation provided by the framework, which groups all the values associated with the same key. And then finally, there is a reduce, again, something that's defined by the user that is applied to all the values associated with a single key. And the outputs of those reducers are exactly what constitutes the output. If you have any questions either about this slide or at any point, please raise your hand. Feel free to interrupt me. I do like interactive presentations. This is more fun this way. So we do have plenty of time, so don't hesitate to ask at any point. Let's take a look at an example. Let's count all the words on the internet. Our internet connects of 4 pretty short websites in this example. So the map function simply splits each text into individual words and attaches the count. So given a website that says my dog, we're going to produce my with a count of 1, dog with a count of 1. But from the website that says dog, dog, we're going to produce dog with a count of 2. This is then grouped by key, and the reducer is just adding up the counts. This way we have counted all the occurrences of any word in this input collection.
So it's invariant under permutation. Permutation doesn't change.
Yes, the reducer typically is given the values in arbitrary order initiation. This is true. Yes?
So if the reduction operator is not associated but floating point addition, you get what you get.
Yes, exactly. Yeah. So I think it's...
So maybe it would be helpful if you could repeat the question when they ask us if they're recording it. That doesn't
Okay, so there were questions about the whether the order to the reducer is arbitrary, or like is it any specific one? And the answer is the reducer has to work no matter what the order of entities or the values is. And so yes, so if it's not associative, you may get different results depending on the order in which the values are being given. Yeah, those are good questions. So this all looks simple, but if you think about it, it's actually pretty. MapReduce allows you to do a pretty complicated computation. Like imagine you want to count the occurrences of words in a gigantic collection, and you don't have a framework like this. Then it's of course a ton of work to do. And here, the mapper and the reducer are trivial things, just tens of lines of code each, and you can actually the framework does a lot of work for you and simplifies large-scale processing by a lot. So how do we achieve fault tolerance in a system like MapReduce? The short answer is write intermediate data to disk, so whatever a mapper produces is saved to disk, and then replicate so that it's not just one disk, because that could fail. If you're using 1,000 disks at the same time, of course, there is a fair chance one is going to fail. And so, of course, without going into details, as long as you have the input to the reduce persisted, then if anything fails, because all that a mapper reducer knows is its input, you can simply restart what it's doing when it fails, and it's expected to produce the same or equivalent result. So here, fault tolerance is done entirely on the framework side. One issue with writing MapReduce pipeline is the so-called curse of the last reducer. And what this means is that if you run the computation like this, and you're going to monitor progress, very often you're going to see a progress bar like this, where it's almost at the end, but it stays like this for hours. And the reason is, well, there are many reasons for this phenomena. One is that you have to make sure that there are no hotkeys. There is no reducer that goes through a huge fraction of data. In the example before, there would be a reducer counting all the occurrences of the. That one would probably be quite overloaded. So you probably would need to do something smarter there. And then if you add preemptions on top of that, you have to make sure that the individual work items, what each reducer is processing, is also not too much, because if your reducer has processed 5 gigabytes of data, then it gets preempted, you lose a lot of progress. So this is still something one needs to take into account. And then this is also combined with the additional challenge that you're only getting a fraction of each machine. So some machines may be particularly slow, and this further may make this work imbalance problem worse. So this best works if the actual individual work items are very small. Then it scales in the best possible way. Now let me also give another example, which is Pregel. It's a system that was invented 2 years after MapReduce and was designed for graph processing. I'm not going to go into details. I'll just to give you a sense. This is just this one slide. Pregel is a similar system, again, one that's designed for fault-tolerant large-scale graph processing. And in Pregel, the framework is actually aware of the fact that you're working with a graph. So the model actually reasons about vertices connected by edges. Each vertex has its internal state and a list of neighbors. And the computation runs in so-called supersteps. In each superstep, each vertex receives messages sent in the previous round. Then it updates its state. It may update the list of its outgoing edges. And then it sends messages to other vertices that are delivered in the next step. If you're working on distributed systems, you may be wondering whether you can send messages not along edges but arbitrarily, and the answer is yes. There is no restriction. The edges is mostly like a syntactic sugar. They don't restrict communication. And if you think about the system, it's actually, in theory, it's essentially equivalent to MapReduce, but it provides it provides a better language to work with if you're solving a graph problem. Yes?
I think in distributed computing there was something, I'm not sure if it's before or after. I mean, it's a kind of, it's not local because you can send also not through edges, but there is like
it's similar to congested.
Just a click.
Yeah, congested click is
But that was only in 2010. I thought it was much earlier. This distributed computing.
Yes. So
approach.
this is empirical work. This work is an actual framework that has implemented and with an actual algorithms. This is indeed similar to like congested click other distributed models, but those are theory concepts that were studied before. I think there is also the BSP model that Parallel is implementing. So yes, the implementations came later.
May I ask you? So if you generalize and you allow not only the neighbors to send messages, but send a message from a node to any other node, then how do you know how much to wait until you receive the message that is sent in the previous superstep?
In the implementation, there is typically a manager which coordinates all of that. So basically, I don't know exactly how it's implemented, but if there is a manager that centralizes this, you can imagine that it knows exactly. It can take care of making sure that everything has been delivered before we say yes, this route has been.
I guess with performance overhead, right? Because you centralize.
Yeah, I mean there is. Okay, so thinking about it, I think
because
you can.
Here, if you know all your neighbors, then you can simply wait, right? And as soon as you receive all the messages, then you say, okay, I'm done. I'm gonna move to the next step. But if you don't know which nodes are the centers, then you have to coordinate with some central entities.
Well, actually, maybe you can even do this in a distributed way, where simply in order to send a message, you're gonna write your message to some disk under location messages for vertex X, and basically at this point, every vertex needs to say, okay, I'm done with sending my messages. So the manager just needs to get like a single bit from each vertex, and then it can say that this route can finish. Also, there are multiple vertices on a single machine, so it's essentially then the managers knowing that okay, every machine has told me that every vertex on each machine has completed. So that's often not too much communication. But it is true that synchronous computation in general is giving us a huge slowdown compared to any form of asynchronous. Now, this is actually this actually leads to a big question of how to do asynchronous computation that at the same time provides fault tolerance. This is, I think, a big open question. I will actually be talking about this later on. But yeah, it's true that those are some real challenges. Okay, we can move on. Okay, so if we now take a look at MapReduce and Parallel, and we go back to our initial goal, well, it seems that those frameworks, to some extent, solve the challenges that we have outlined before. So those systems can deliver fast solutions because they're very easy to scale horizontally. You can get better performance by adding more machines to your computation. It's arguably simple because the frameworks do a lot of heavy lifting for you, and also they provide fault tolerance, and so it's not something you have to care about. So a lot of the difficult stuff is abstracted away. They're also cost effective because, again, since they're fault tolerant, they can work decently on low priority resources. They can tolerate preemptions decently well. So if you look at it from bird's eye view, it looks like many of these problems have been addressed. But of course, the big remaining part is the algorithms. Like we still need to have efficient algorithms in those systems, and we also need to implement them, and only then we would be done. And so this brings us to the second part of this talk, which is the Ampc model. The Ampc, which starts for massively parallel computation. And this is a theory model which captures both MapReduce, Pregel, and also several other similar systems that have been developed before. Ampc was defined in a series of work starting from 2010 paper by Karlov-Suri-Vasilevitsky. And it's a model of computation that happens in synchronous rounds. We have a collection of machines, and then in each round, every machine receives messages from previous rounds. Then every machine performs arbitrary computation, and then it sends messages to other machines to be delivered in the next round. So it sounds almost like Pregel. It also captures the MapReduce in a, well, not very difficult to see way. And then if you look at maybe the beginning, initially we assume that the input is simply randomly distributed across the machines that participate in the computation. Now, let's take a look at some parameters and restrictions of the model. So we denote the input size by n. We have p machines, each of size s. And the total space in the system, so the total space of all the machines, is barely enough to store the input. That's required, because otherwise it would be hard to imagine you can process it. Sometimes you can allow a bit more total space than the input size. This depends on the actual problem you're solving. And now come the important restrictions. We assume that the space per machine is strictly sublinear in the input size. And this captures this idea that your computation needs to be balanced. You cannot have like one machine doing all the work, but you actually want to parallelize across multiple machines. And then every machine, there is also a bound on communication. Every machine sends or receives data of size at most s in a single round. So a machine can read or write at most the volume of its local memory in every round. The goal is to minimize the number of rounds. Okay, so that's the end of the definition. Any questions about it? Yes, Siddhartha.
From a practical perspective, I assume you also worry about the amount of computation that happens within each of the rounds.
Okay, yes, I have this. Yes, this is a good question. I do have this on the next slide.
And my question is, so you send a message of size S, but you can send multiple messages?
Yes, good question. So the question is whether a single message can have size S. So the total size of all the messages sent by a machine, it has to be at most S. So you can send either one huge message to one machine, or you can send a huge collection of small machines to many. But the total of those sizes has to be at most S. Thank you. So you may be wondering, yes, as Siddhartha is wondering, computation is unbounded. Can you exploit this in a strange way? Can you solve, well, you can solve an NP-complete problem on a single machine. Can you cheat? Turns out we don't really know whether you can, like, I don't know of any algorithms that would abuse it in a very bad way. The only examples that come to mind is that some de-randomization techniques have used a ton of computation on a machine to de-randomize the randomized algorithm. But other than that, I did not see algorithms where actually this would be exploited in a strange way. The other thing I would like to mention is that the goal here is to minimize the number of rounds, which is sort of like reducing parallel depth. And then if you're wondering what is the analog of work, I would say that the best one is the communication. The total communication roughly corresponds to the total work because the algorithms in most cases run in near linear time to what a machine receives in a round. Which is problematic because if you think about it, like it's not just the depth that you want to minimize, you also care about the total work if you're interested in achieving low end-to-end running time. All right, so you may also be wondering how powerful this model is. So if you compare this to, say, PRAM, a standard model of shared memory parallel computation, Ampc can simulate PRAM. That should not be too surprising given that you can do a lot in a single round of Ampc. And in particular, well, you can simulate one step of PRAM. But ideally, you would like to do much better than what PRAM does in an Ampc computation. And in fact, you can in several cases. So for example, computing XOR requires a logarithmic number of PRAM steps because you need to do some kind of binary tree style reduction. But in Ampc, you can do this in just 1/epsilon rounds because you can be reducing using a topology which is like a tree of arity n to epsilon, right? You have your bits scattered across the machines. Every machine XORs what it has. The data shrinks by a factor of 1 plus epsilon. You redistribute and you repeat. And in terms of lower bounds, you can actually show unconditionally that XOR requires at least 1/epsilon rounds on Ampc. But the more commonly used lower bound in Ampc is a conditional lower bound of log n rounds that I'm going to show in the next slide. So the hard canonical problem in Ampc is the so-called 1 versus 2 cycle problem, where this is a promise problem. Here the input is promised to be either a cycle on 2n nodes or 2 cycles of n nodes each, and your goal is to distinguish which one it is. It is widely believed and conjectured that this requires log n rounds, and this then translates or can be used to show hardness of other Ampc problems, conditioned on this being true. Why is this the case? Well, intuitively, in the only thing you can do in Ampc, it seems, is that in I rounds you can actually communicate with nodes that are 2 to the I hops away by some kind of graph exponentiation. Like initially, if your graph is like, if those vertices are stored randomly across multiple machines, everybody knows their neighbors, but then you can join on common neighbors, find paths of length 2, then you can join on the endpoints of those paths, find paths of length 4, and so on. And nobody has found a way to do anything meaningfully better than that. This is where this hardness is coming from. Yes?
So I've always, is there any hope of proving this with some information, or is this as hard as beavers and
I am not an expert of what exactly it would take to prove this. Maybe there's someone in the room who would know, but the way I remember is there is one side of this conjecture that if you were able to prove it, or maybe disprove it, this would have very deep consequences for long-standing complexity theory open questions. So I think it may be tricky I think proving it may actually be a very tricky task because it is related to known hard problems. Okay, and then in terms of graph algorithms, in Ampc there are 3 different regimes that people study. First is the superlinear regime, where the space per machine is superlinear in the number of vertices in the graph. Second one is when the space per machine is linear in the number of vertices in the graph. And because in Ampc we want the space per machine to be sublinear in the input size, which is the number of edges, those 2 regimes only make sense if the graph is quite dense and the number of edges is like bigger by n to a constant factor than the number of vertices. Otherwise, you can just put everything on a single machine and solve your problem. This middle regime, the linear regime, is actually very similar to congested clique. There is known equivalence with some caveats between those settings. And then this rightmost one, this is the most challenging one, where the space per machine is strictly sublinear in the number of vertices, but it's also the one that has been studied the most. There is a lot of interesting work on giving efficient algorithms in those settings. And if we look at algorithmic results, here is how those regimes compare. In this first setting, the one where we have quite a lot of space, a lot of problems are solvable in constant number of rounds. And if the further we go to the right, the more restricted the setting is. In this sublinear regime, for many problems, we don't actually know whether the existing solutions are the best possible or whether we could do better. Now, this slide is from a few years back. I apologize if some newer results are not included, and I also feel bad for not including the citations because some of those beautiful results are from people in this room. So there has been a lot of work going into getting to this state of matters.
I mean, just about the delta plus 1 coloring, is there, I thought that there is in PRAM, there is a log star. Oh, it's not PRAM. There is a log star algorithm, so why
there is log star. Okay, Yossi's question is, there is log star depth algorithm for delta plus 1 coloring in PRAM. Why don't we have at least log star here? I do not know. I would have to check, because I do remember at least a few years ago this was definitely the state of the art. Unless I badly messed something up.
Maybe it's only, I forgot, maybe it's only for recycle.
Cycles,
I
think it's for cycles.
Okay, so that's cycle. Okay.
Okay.
Yeah. Okay. So then, yeah, this is for general graphs, which is why it's more challenging. Yes, Phil.
So right now the model equates sort of local memory on a machine and amount it can communicate around.
Mm-hmm.
What if you separate those two, right? What if you said, oh, I can only communicate out of the epsilon because I don't want to be like communicating like crazy, but I can actually store n maybe or something, right? Does that help?
Okay, so the
question
balance
on the communication, or are they balance on the space, or both?
Yes, this is both. Okay, so the question is, what happens if we don't have the same bound on the communication per machine and space per machine? Yeah. Okay, so the honest answer is I don't really know, but I think that off the top of my head, it does not seem to be like helpful to have more space per machine. It seems that communication is the bottleneck here. For example, if we look at the 1 versus 2 cycle conjecture, having I'm not sure whether with more space per machine you would be able to do meaningfully better, because you're simply missing information that you could need to do better. But for other problems, it's difficult for me to resolve this off the top of my head. I'm a bit concerned that maybe you would be able to diverge from the spirit and actually start aggregating a big part of the graph on a single machine, which is against the principle of the model. But I don't know. Maybe with the bounds that you have, this would not even be meaningfully helpful. Maybe now that I think about it more, the number of rounds is typically very small. Like it's like polylogarithmic. The space per machine is n to a small epsilon. So probably you wouldn't be able to get a lot more data in the number of rounds that you're allowed to run. So I think it would not be too helpful to have more space per machine than the amount of communication, but this is what it feels to me right now.
So you could take that out of the model and you just potentially say they have unbounded space or something locally.
Perhaps, but yeah, I don't understand the full implications, but it may be possible. I have not heard this question being asked before, so it's something that one would have to think about.
But then the question would be why the input is distributed among all machines. Why not to put all the input on a single machine? I guess that's the reason. Maybe.
Any more questions? Okay, let's move on. So the sad realization that I had while working on those slides is that, to the best of my knowledge, I don't think any of those beautiful algorithms have been implemented. And I do not mean like implementing them literally. I wasn't even able to think of ideas from those algorithms that would actually be meaningfully helpful for implementations. And I started to wonder why, and I came with 2 reasons that I would like to share with you. So first is that, as you can see from the 1 versus 2 cycle conjecture, a fundamental challenge in Ampc is dealing with high diameter graphs. Like in I rounds, you can maybe discover 2 to the I radius neighborhood. But if you look at diameters of real world graphs, they're typically very small. So the challenge of working with high diameter is a challenge when you're working with worst case graph, but it does not seem to be a challenge that you encounter working with real data. Now, you may be thinking, what about road networks? And I think the short answer is, I don't think we have road networks that are large enough that you necessarily need to process them on multiple machines. And then the second challenge in Ampc is that something I mentioned is that the model bounds the communication in each round, but it does not ask to optimize it. So if we look at two algorithms, one that runs in square root of log n rounds, and this is a complexity for several basic problems like MIS or maximal matching in MPC, and uses slightly superlinear communication. And if you compare this to what you can often get in MPC quite easily, log n rounds and linear total communication, according to MPC definition, the green algorithm is better because the number of rounds is smaller. But if you think of communication being the total work of the algorithm and you assume that the number of machines is fixed, well, the running time is then roughly the work divided by the number of machines. So the right algorithm is actually better. So it seems that in some sense the model may not fully capture the actual performance characteristics of the algorithms when applied. Yes?
Are there better bounds for MPC algorithms if you bound the radius or the diameter of them?
I am aware of one, which is for connected components you can get log diameter plus log n rounds. So I think there may be also some and I think on forest connectivity you can get log of diameter rounds. But I think those are the only algorithms that actually can benefit from low diameter graphs in their round complexity. Yeah, that's a good question. Okay, so we've seen MPC model. There is an interesting line of work. There are still challenges with applying those ideas in practice. So what do you do when your model is not perfectly capturing the reality? Well, you come up with a different model. And this is what I'd like to talk about for the next 10 or 15 minutes. And so I would like now to introduce the adaptive massively parallel computation model. This is a slightly richer computation model that is designed to address some of the challenges that of the MPC model. Ampc, in short, is MPC plus a distributed hash table. What I mean by a distributed hash table, also known as a key value storage, is just a service, a collection of machines. It stores key value pairs. You send a query with a key. What you get back is a value. Very simple semantics. Now, the cool thing about an operation like this, retrieving a value corresponding to a key, is that modern systems provide hardware acceleration to those type of reads, even if you're reading from a remote machine. So the lookup latency of a query like this can be as low as a few microseconds, which is just an order of magnitude smaller than reading from local RAM. So this is a very low latency operation, and we would like to leverage it to design a more powerful model. So the Ampc model works as follows. It also has a collection of machines that perform synchronous computation. There's input of size n. There are p machines, and each has size s, which we would assume to be n to some constant epsilon. Now the difference is that all the messages sent in one round are being stored. Can you see me? Okay, I can point here. All the messages stored in one round are being saved to a distributed hash table, and then in the following round, the machines can read from this hash table. So instead of being given a portion of data to process, the messages, it can adaptively choose what to read. It may read a value, and based on that value, decide what to read next. Yes?
When you said the cost is 1 to 3 microseconds, does that take into account the size of the message, which can be very large?
That's for small size messages.
Okay.
Yeah, of course, yeah, there's also throughput, but yeah, the latency for small messages is just a few microseconds. Yes?
What if all machines would like to write to the same hash table, to the same location in the hash table?
Yes, so basically what happens here, so the question is, what if two machines want to write to the same location? The way this works is that in a round, let's consider this middle round, there is a read-only hash table, which is the input, and there is a write-only hash table, which is the output. And so once the run finishes, the write-only hash table becomes a read-only input for the next round. And in the model, you can simply define what happens if you have conflicting writes. I think you can just disallow that, and that's still fine. Maybe you can provide some resolution of those cases. It doesn't seem too meaningful. I mean, unless you provide some very strong operation for resolving conflicting writes, I don't think it meaningfully changes the model. But the other options I think the two options that we considered is either disallowing or just saying that in the next round you access all the values that have been provided for this key.
So in particular, you cannot count how many appearances of the same key appears in one round.
That would be too much. Yeah.
So adaptivity sounds very bad in practice because one machine could take n to the epsilon time to decide which locations to read. Do you mean full adaptivity for that much?
Yes. So yes, this is a good question. So what if? Okay, I have this 2 slides later. Let me go back to this in a sec. There are some natural questions. How does this model compare to Ampc? First of all, fault tolerance. Well, as soon as you have a fault-tolerant distributed hash table, which is a well-studied problem, you inherit the good properties of fault tolerance from Ampc because any failing worker can just restart from scratch. It sees the very same state of the input because the input in this round, this hash table does not change. So if you restart later, you're going to see the same input, and you can redo your computation. And then you may be wondering, can you allow writes within a round? So then not only have like a read-only input hash table, but one that you can also write to. It's in principle possible, but then it makes fault tolerance very difficult to reason about, because what if some worker made some partial change but then failed? How do you understand where to continue? But I'm actually going to go back to this idea later in this talk. But a priori, this is quite hard. And in terms of how realistic this model is, yes, you may be wondering, this was a good question, what happens if a machine makes a very long chain of reads that are sequential? Well, we did have experiments that were checking for this scenario, and actually this does not seem to provide a big slowdown. I believe the reason is that the individual latency of a read is very low. So you can imagine having hundreds of thousands of round trips per second if your latency is as low. And then you may be also wondering, what about read contention? What if everybody wants to read the same value? Again, under some reasonably natural assumptions, you can show that there is actually no read contention in a probabilistic setting. Let's not go into the details of that in the interest of time.
But that doesn't sound right to me, right? I mean, unless I'm misunderstanding what the keys in the distributed hash table are going to be. Right? I mean, you talked earlier about hot keys and stuff like that. Why don't you have hot keys here?
Here, I think the reason is, I think this is the key reason, that you have typically have fewer. Okay, so the total input size is the number of machines times space per machine. Typically, the number of machines is smaller than the space per machine. And so each value can be accessed by so what's a good example? So each value, because the input is read-only, every machine would access each value at most once if it caches what it reads, right? So then each key is going to be read at most, 1,000 times, because if you have 1,000 machines. So this cannot get unbounded because only one machine is reading each value. Each machine is reading each value at most once, and if you store those key value pairs randomly, this is actually averaging out in a nice way. I think the key observation is that it's not that you can be reading each value all over again. If you cache what the machine reads, then there is a very well-defined cap on the number of accesses to the same value. Okay, so let's take a look at our favorite problem, distinguishing between a cycle and 2 cycles in Ampc. And let's take a look at the algorithm in the Ampc model. the idea here is that we would like to shrink each cycle by a factor of n to epsilon in each round. And if we manage to do that after a constant number of rounds, the cycles would fit on a single machine, and we can decide easily whether it's 1 cycle or 2 cycles. And how do we shrink a cycle? Well, it's actually pretty easy. If we store the cycles or the graph in a distributed hash table, and we sample each node with probability, say, n to minus epsilon, so the green nodes are sampled, then each sampled vertex can actually find its 2 nearest sampled neighbors in just 1 round. And this is exactly this case where we read something, find our neighbors, based on the neighbors, we find neighbors of neighbors, and we have this sequential chain of reads that allows the green node to see the neighboring green nodes along the cycle in just 1 round. So if we sample each node with probability n to minus epsilon, we can shrink each cycle by an n to epsilon factor in 1 round and solve the problem in a constant number of rounds. As opposed, this is in sharp contrast with the Ampc conditional lower bound of log n rounds, which means that Ampc is strictly stronger than the Ampc model as long as you assume the 1 versus 2 cycle conjecture.
So just a question kind of about the history of this model. Like, did somebody build something like this and a theoretician noticed, hey, this solves the 2 versus 1? Or was this model designed to find a model that would solve the 2 versus 1?
Yeah, great question. Yeah. So, okay, the question is, how was this model designed? So, I think that the history dates back to the work of my colleagues on the graph mining team at Google. There were actually several applications where they realized, oh, if we run this MapReduce pipeline and we have access to a distributed hash table next to it, we can actually solve some problems more efficiently. And so this was done as without any theoretical reason, but this was just exercise in implementing efficient large-scale pipelines. This was used for affinity clustering, so like a highly scalable graph clustering method. This was also used in like a connected components pipeline. They also observed a way of actually leveraging a hash table. And then later on, we had this idea, well, can we actually formalize this and turn this into a model? And this is how Ampc was born. So it started with a system, and then it was, this idea of combining MapReduce and a hash table, and then it was captured in a model that was formalized into Ampc.
But you mentioned that in practice there are no high diameter graphs.
True, but so yes, it's true that this is now maybe this first result is not the most relevant in practice, but actually, if you look at the algorithms, you can also leverage this idea for lower diameter graphs, which I'm going to talk about in a sec. Okay, so. Yes, exactly.
So if you only allowed to read it once, then there is no extra power.
Yes. I mean, yes, because then you're gonna just this is probably gonna be equivalent because it's almost like sending messages. Maybe there's gonna be a small difference that you would make it easier to send some worker to send data to everybody else. So I'm not exactly sure whether this would be the same, but the most of the power comes from the fact that you can adaptively read, hence the A in the model name. So if we look at some popular algorithms that have been studied in an Ampc, it turns out that in Ampc you can solve those canonical problems in just a constant number of rounds, very often using much simpler algorithms than the Ampc counterparts. And it's actually quite interesting that it's not even easy to come up with a graph problem where you cannot give a constant round Ampc algorithm, which, I mean, of course, without going into pretty contrived examples. And then as a follow-up to our work, there has been several other papers showing that you can achieve very low round complexities for many problems. One interesting open question is connected components, where if you insist to have linear total space, you can almost get constant rounds, but not quite. You get 2 to log star n. So there is this tiny gap still remaining. But there has also been progress on many other graph problems. In terms of, yes?
There is probably a problem which is probably cannot be done in constant time?
Well, there is this lower bound, which says that, again, for 1 versus 2 cycles, you can't do absolute constant. You need 1 over epsilon. But I don't think we have unconditional super constant lower bounds if epsilon is assumed to be a constant. Yes?
So for most of those Ampc algorithms, are most of them using randomization or not? Or
good question. I think many of those are. If I have time, I will maybe present connected components in Ampc, and that one leverages randomization heavily. So actually an interesting question whether you can get rid of that. In Ampc, I know that many algorithms have been de-randomized. I'm not aware of related results for Ampc. And then on the lower bound or the complexity theory side, this was also recently shown that the complexity class reach UL is not strictly contained in Ampc. And I decided to include it because I found it interesting that people now study Ampc also from the complexity theory point of view. But I acknowledge that I do not really understand what are the implications and what is even actually the actual definition of reach UL. So please don't ask me about the details. You can check in the paper. But the point is that there is also like a formal complexity class defined around the model. Okay, so we have 20 minutes. So let me maybe go a little more quickly. So we have implemented Ampc. Let's skip the details of how we did that, and we implemented some algorithms, and we ran them on real-world graphs of up to 226 billion edges. And we found that not only they use significantly fewer rounds, but this model also translates to actual speedups in practice. Now the important thing is that in this column, in those 2 columns use very different algorithms. This one is using an Ampc-specific algorithm. Of course, you cannot have the same algorithm in the MPC model. Here we typically use like a simple baseline MPC algorithm, which was the best MPC algorithm that we could think of for the comparison. Okay, so let me try to get through this example of how do you design algorithms in Ampc model. We should still have enough time for that. And I would like to show how you solve connected components. This would not be the fastest existing algorithm. We're almost going to get there, but the fastest one is actually a little more complicated. So the first step is to solve the forest connectivity problem. So connected components, if your input is a collection of disjoint trees. Step 1 here, you want to turn each tree into a cycle, so like the Euler tour of a tree. And you can do this by splitting prove by picture. You can split each vertex such that if you do this transformation locally on each vertex, your tree becomes a cycle. And now we have cycle connectivity problem. And we're going to apply the idea from 1 versus 2 cycle algorithm, where you can shrink each cycle by a factor of length n to epsilon in a single round. So you can repeat that. The problem now is in the 1 versus 2 cycle problem, that was enough. We shrank everything to small size, and we're done. Here in the generalized problem, we may have, say, n over log n cycles of length log n. And for an input like this idea does not really help. Like you're gonna sample very few cycles, you're not gonna make progress. So we still need to deal with the case where each connected component has small length. And this is where we're going to use randomization. And I think this is a nice canonical example of the types of the flavor of algorithm that you implement in the model. So what happens here is we now want to find connected components. We have a graph which is many cycles, each is relatively short. So each vertex is going to choose a random priority uniformly from 0 to 1. And then every vertex would traverse the cycle, but it would abort as soon as it finds a vertex with higher priority. So only the highest priority vertex on a cycle is going to traverse the whole thing, and it's going to say, OK, I found a connected component. And if you look at the analysis, on a cycle of length k, the vertex with the I largest priority is going to traverse an expectation k over I vertices. If I have the third largest priority, there are two vertices that have higher priority. I'm going to, in expectation, traverse the third of a cycle before hitting one of them. And this is how you get this bound. And using a harmonic sum argument, you can see that you can do this for all the cycles at the same time in expected n log n communication or n log n total space, because space and communication are the same. Questions?
But the number of rounds is larger.
This is Ampc, so this is one round.
Oh, this is in one round.
Yes, this is a one-round algorithm now, where every vertex is traversing a cycle. The assumption here that those cycles have been shortened and there is nothing that's super long anymore. Okay, so we have solved forest connectivity. Now, how do we do general graph connectivity? Well, step one is, again, a reduction. We ensure that max degree is at most 3. Again, proved by picture. I'm not going to go into details. And now the graph has m vertices and m edges. And now I'm going to do something similar but a little different. I'm going to leverage, actually, forest connectivity here. Again, every vertex chooses a random priority. And now every vertex is going to run BFS or DFS, like whichever search algorithm, that doesn't really matter. And now a vertex V would stop the search in one of two cases. Either I find someone with higher priority, and then I stop and I add a super edge to this vertex of higher priority, or I have exceeded the communication budget, so I've seen n to epsilon other vertices, and then I simply stop. I do nothing. So what happens here? I do m log n total work. The analysis is the same. I also check. I'm also picking a uniformly random variable from 0, 1. I stop if something is larger than me. And then the super edges that I find, they form a forest because there is a super edge from a vertex to a vertex with larger priority. There can be no cycle. And then the probability that a vertex is a root in this super edge forest is just n to minus epsilon. The only way for me to be a root is if my priority is larger than the priority of n to epsilon vertices that I explore. So that's unlikely. So if I find connected components of the super edges, that's forest connectivity, I reduce the number of components by an n to epsilon factor. And then I can repeat that 1 over epsilon times, and this all runs in Pauli of 1 over epsilon rounds altogether. If you don't, if you miss some of the details, don't worry. This is just to give you a flavor of what is the way in which you reason about those algorithms. Yes.
Sorry, I don't think I follow the details, but it seems like fundamentally previous models were all push models, right? That is, if there's distributed information partitioned amongst different nodes, and in a round in all the previous models, a node can decide to send some subset of what it has to others, right? Here it seems like the reason why you're able to get all these round ones is you have a pull model. There's this distributed information. I can just choose to go pick this, pick that, pick this, pick that. And so why is this meaningful? That is, so it seems like there's a lot of essentially rounds of communication that are happening here because I can keep pulling, figure out something, and then I say, oh, I want to pull this, I want to pull this. So why would that be meaningful to count it as one round?
Okay, so the question is, summarizing, is that the Ampc model feels like a push model. You send messages to some other machine. This is more like a pull model where a machine decides what to read, and this is true. Now, I understand the concern is it fair to assume that multiple values being read in one round is still like fair? I think the only justification I can give is that empirically it seems to help. I mean, the way this way of reasoning empirically leads to more efficient algorithms, and I understand that it may not seem as parallel as the previous model, but I think one way you can think about it is that it's some kind of a mixture between a synchronous and asynchronous model. And so we partially desynchronize the model, which leads to better communication. Whether the naming is the best possible, because there are like sub-rounds happening within a round, and I agree that this is happening. But I believe the partial desynchronization is what gives rise to those speedups. Yes? Phil?
So the 1 to 3 microseconds, that is independent of the size of the distributed hash table? I mean, like if I have something tremendously large,
well, this
I
is.
still want, small messages, so it's not this earlier question.
I think this is the case because those huge hash tables, they're going to be served by multiple machines, and so if you have some kind of hash, you can use your hash function, and you know exactly which machine to go to. So the fact that it's one machine out of 20 versus one out of 10,000 does not seem to matter as much, because you know exactly where to look, and in the end, the latency is for going to a specific machine and fetching from it.
But you said it was faster than going to your local RAM. So
no, it's not much slower. It's not faster. It's like only a little slower.
So when you do an RDMA, is the bulk of the time then in just getting that machine, and it doesn't matter. Like I could do a lookup into something that's not cached, and I still get that kind of performance.
Sorry, I did not get the question.
So you're using RDMA to implement this, right? So basically, there's the time to sort of notify this other machine that you want this particular value, you want to do a memory read on their behalf. And there's a time to do that memory read. And it seems like the time to actually do that read on the far machine depends on how well you're caching the data, right? Like I don't want to have to actually go out to the far machine's DRAM to get that data, right? Hopefully if I have a distributed hash table, that's small enough to fit in some levels of the cache on that far machine, then I'm going to get a much better performance than if it's not. Is that not true?
I see. So, okay. So the question is, does this matter depending on whether the hash table on the remote machine fits in cache versus doesn't, right? Yeah. I am, to be honest, not an expert on the technology to be able to answer this detailed question. Something I can check. Lakshman, yeah.
Wouldn't it only add like another 100 microseconds or something? No, not 100. Like the cost of a cache miss, right? I think the dominating cost would be the cost of getting to the other machine, and not the cost of the cache miss on the other machine. Because I think these things are all they're bypassing the caches of the host machine. They're accessing DRAM themselves, like through the RDMA controller.
No,
I have a fuzzy knowledge.
They are touching the cache, but it doesn't matter much. Like the network is probably 2 microseconds, then the cache is probably 100 nanoseconds. If it's cache, it's probably 2 nanoseconds. If it's not cache, it's like 200. But it doesn't matter, because the network is 2 microseconds. And by the way, in terms of cache, I think RDMA do touch the cache. Otherwise, you get false results. So there's a cache coherence running there, but it does not change much. It's more about the correctness. So because if there's no cache coherence, it will be incorrect. So they have cache coherence, but it does not change much in the performance.
Okay, so as long as you're fitting in memory, period.
Yeah, if it's in memory, it's all right.
So okay. It's bigger than
memory. That's the problem.
So to summarize the discussion for folks viewing online, I think the consensus from the experts is that whether it's in cache on the remote machine or not, it's not going to matter, because the cache miss cost is still like much smaller than the latency of actually network communication, which is a couple of microseconds. Yes, you had a question?
Yeah, I still, following the previous two questions, I'm still a little bit, I'm just wondering if this Ampc is not, in some sense, a bit cheating, in the sense that you take something which is inherently sequential, and the next decision depends on the previous decision, the next decision is dependent on the previous decision, and so forth, and then you call such a long chain as one round. Because you, in some sense, you take something which is inherently sequential, and you call it one round, because adaptively inherently sequential in that sense.
I think the other comment is that you have at most n to epsilon sequential steps, and you're actually free to tune epsilon. So you can, there is this cheap sequential steps, which the n to epsilon ones, and there are the expensive sequential steps, the rounds of the algorithm. And of course, You have to choose your epsilon to balance the two, but I think in practice it turns out that relatively large epsilon is still giving us benefits because of those small steps are so much cheaper than the big sequential steps, which is like a full synchronization across all the machines. I think this is where you have to like play with the parameters, and the difference is massive. Prashant?
Do you have to deal with like skewness issues in the distributed hash table, like if you're just using sharding or something like that, and some machine gets more keys than others?
I think random sharding suffices to deal with that, from what we've seen. Yes?
To address the question of around versus, the difference between around in this model and the previous model, do you have information about or comparisons about how many total accesses they make, or the total size of communication?
Yes, we do have plots in the paper. In the interest of time, because I still have several slides to show, let me take this offline. But yeah, we did measure that. Okay, thanks for all the questions. Yeah, I love getting questions. And so yeah, summing up, we saw an algorithm that gets constant number of rounds and log-in communication. You can improve a little bit, but let's move on, because I still wanted to go on the what's next topic. So if you looked at our empirical results, they have been on a hyperlinked 2012 graph, which is a graph of about 200 billion edges. But if you look at Lakshman's PhD thesis, this is a picture from the thesis, graphs of this size can well be handled on a single machine. Like if you use a terabyte of RAM, maybe some lightweight compression, you can still squeeze this big graph on a single machine. And it looks like single machine computation not only can match the running time of a distributed computation for a problem like this, it's also using many fewer threads. So you may be wondering, okay, I was talking about like over an hour about distributed computation. Now it looks like a single machine can be as fast. So what's going on? Why do we even care about running on multiple machines? And it's a very good question, and I have two answers to that. The first one is that in those two settings, the running time is measured a little differently. On a single machine computation, you load data from disk to RAM, then you start your computation, you measure the running time, and then after you stop measuring time, you save the result to disk. In a distributed setting, you typically, I/O is very cheap because you have the combined bandwidth of multiple machines. So you often start measuring time from the time that you load the data from some cloud storage, and you also include the time needed to store the results to cloud storage. And so this is not exactly apples to apples. And if you think about the actual end-to-end running time, the fact that you can compute something on a single machine when the data is in RAM is not really the end-to-end result, because you typically don't have the data on your machine, but you have to load it from somewhere and only then process. And this loading time can actually be quite a lot, right? Like loading this hyperlinked 2012 graph, even assuming a pretty good 100 gigabit network, would take over 2 minutes. And then it would take about 8 seconds to find connected components in this graph on a single machine. Which is a paradox, right? Because it means that if you really care about end-to-end running time of your large graph computation, you don't have to invest in CPU, you don't have to invest in RAM, but you should get a really good network controller. And this way, you're going to get the best running time. Now, the other thing, that has to be taken into account is that this is what I call the single machine capacity cliff. When you do computation on a single machine, you can only scale it so much, but at some point you hit the amount of RAM in your machine, and then you're done. You're not able to handle any bigger data size. And from the plot I showed before, this phenomenon happens that as soon as your data size is a little larger than what you can handle in a single machine, the performance per thread drops dramatically. So this is actually a very real and actually quite a frustrating phenomenon that we don't seem to have a way to have some kind of graceful performance degradation. Right now, when the data is a little too large, you pay this massive penalty in the running time.
So use 2 machines.
Well, but then the communication between them would be like a huge bottleneck. And yeah, I don't think using like a couple of machines would be an easy solution here. So based on this state of matters, I was wondering, okay, what is it that we could do next? And I came up with 3 pretty natural ideas. They're meant to be like discussion starters. So idea number 1 is we can try to push the cliff further. So we can try to squeeze more on a single machine. So we can use space-efficient algorithm, work on compressed graphs, or we can leverage external memory, SSDs. Like Lakshman is giving a talk on Wednesday on that topic, and I think that's a very interesting direction. Idea number 2 is to consider a hybrid model, to try to take the best of both worlds. So use a distributed setting to shrink your data somehow. Maybe I'm thinking of some analogs to data reduction or kernelization, which was being used when working with like NP-complete problems, but you can apply it here. You can shrink your data and then solve the core of the problem on a single machine. And if someone is thinking, well, we have the streaming model, I don't think this is addressing a problem at least I care about a lot, because a streaming model for graphs typically assumes n polylog n total space, so polylog n space per vertex. From my experience, I am yet to see a graph problem where using average degree of more than 50 would be useful. If you have one, I would really love to hear about it, but I've seen it repeatedly that even if your data appears to be denser, throwing out additional edges does not seem to matter. We can safely assume that graphs are very sparse. And so models that work for graphs of more than n polylog n vertices don't seem to be, at least from my perspective, broadly applicable. Again, this is my point of view. Happy to learn about applications where dense graphs are actually the only right model of a problem. And then a third idea is, let's maybe come up with a new model. There was a lot of discussion on Ampc, and I do think that there is certainly time is right for coming up with a next and better model. One idea that I had in mind, one of many, is what if we allow writes? What if we have this model where we have some kind of shared memory that's fault tolerant, whatever you write to it would stay there, but you have workers that can fail in the middle of the computation. It's sort of like concurrent computation, except that a thread can fail halfway. I don't know, maybe this model have even been studied. Okay, Siddhartha is nodding, so I don't, okay, it's okay, you're acknowledging, but, okay.
Studied in the shared memory setting recoverable and durable algorithms where processors can fail and so forth. But not in this setting where you go beyond the machine, right?
Yeah. So there is an interesting question whether those methods studied in some setting can extend to multi-machine, and of course this is just an idea. I wonder if if there are some other models that are on one hand realistic, but on the other hand interesting theoretically, that can help us handle problems on very large graphs. And with that, thank you very much for all the questions.
Time for a few questions. There are a lot during the talk.
So I wanted to get back to the original motivation. So, well, first of all, I had a question. So, does based on any of this work, does now Google fill up spare capacity with other people, with these kind of fault-tolerant jobs? And what's the limit there? Because it feels like, you don't never want to have too high utilization on your machines, and also there is a maybe there's a heat challenge or something, right? You don't want to run all the machines at full capacity. You may not be able to drain the heat that fast or something.
I think it's fine to fill up the unused capacity with low priority jobs, but as soon as you need more for the high priority jobs, the low priority ones would be preempted. This picture was from 2020, so this is already already showing some of the capacity being used by low priority jobs. And even with that, there is still some unused capacity.
So in production environments, they would be willing to run the machines at much higher utilization than they are now. There's no sort of practical.
Well, I'm not an expert on on job scheduling, so I do not know these things for a fact. It seems that I would assume that this is being exploited the best way possible, and I would assume that it is possible to utilize the full machine with the assumption that that some jobs may be preempted with little warning.
One more question.
So I might just be remembering the slide wrong, but I think all the graph algorithms I remember you putting up were like connectivity or like neighborhood type problems. Are there MPC or AMP solutions for like path problems, like shortest paths and things like that?
So the question is, are there MPC or AMPC algorithms for path problems? I think, okay, the first idea, the first memory that comes to mind is Michael's work. Can you answer this question for me, Michael?
Yeah, so Yasmin and I had a paper doing like Thorb's-Wick basically in MPC. It's like you can basically do it. It takes like polylog rounds, which people in MPC don't like.
Yeah. Okay.
I think you, Michal, might have had an improvement slightly, but I forget the details. I don't know anything in AMPC, but I haven't followed the AMPC literature.
Okay, so also to repeat the answer, there is work on shortest paths using polylogan rounds, and this is both from Michael Dinitz, but also Michal Dori has had a paper on this, right?
Yeah, because I think we were doing like Thorb's-Wick stuff, so we were getting like constant stretches. And I think you can get 1 + epsilon stretch using other ideas. And Michal Dori and Merle Porter and people have some results on that.
So it's actually, I think we did think about it. It's not easy, but it will be interesting to see whether AMPC, which seems to be a good model for improving upon shortest paths in MPC, whether this can be exploited. But we don't know the answer.
All right, let's thank the speaker again. Coffee break for about a half hour. Yeah, that was very nice talk.
Thank you.
So were you one of the